similarity with constructions, and this time we're going to look at two additional theorems, the angle-side angle theorem and the angle-angle-side congruence property. If I'm looking at angle-side angle, this means that the side between two angles has to be congruent in two different triangles, as well as the angles on either side of it. So looking at this example, notice how the side that's congruent has the two double marks, and it's literally between the two angles. That is when you can apply the angle-side angle theorem. So if I look at this triangle, at first I see the quadrilateral, and it's easy to focus on the quadrilateral. But we need to see this as two triangles that are backed up together. Because the two triangles are backed up together, they share a third side, and that third side would be congruent to both triangles. So now I have an angle, and the side between them is congruent, so then I can prove that the two triangles are congruent by angle-side angle. If I want to show that these two triangles are congruent, again, we're kind of trying to pull out the triangle in this, and we're trying to make sure that we know two angles. Well, we have a 30 and a 90-degree angle in both of these. And if I look at this, I have the 30-degree angle, I have the 90-degree angle. I know this is 3, and I know this is 3. This is a shared side, and if this is 30 and 90, that means that this third angle is also the same. It's going to be 60 in both triangles. So the included side is actually this 3 because this is 60 and 90 and this triangle. And then this is also 60 and 90 in this triangle. So we have that theorem. If I want to use the definition of a parallelogram, I can also use that to prove that this is happening. I need to show that the length from BO to DO is going to be congruent and AO to CO. So I know the opposite sides of a parallelogram are congruent, so I'm going to build that portion of my reasoning out. Now I have an angle with an included side between the two angles in the figure here and here, so that tells me that those triangles are going to be congruent. Once I've proved that those two triangles are congruent, we know that corresponding parts of congruent triangles are congruent. So I can then move from there to prove that those two diagonals are also going to be congruent. Here are some properties of quadrilaterals. Just giving you some information for this. I suggest writing these down on a piece of paper so you have them handy because there's a lot of properties of quadrilaterals to go through that you're going to need to know. So in a trapezoid, consecutive angles between the parallel sides are going to be supplementary. Then you're also going to have the isosceles trapezoid, where when you have that, the base angles are going to be equal and the non-parallel sides are also going to be equal. If a trapezoid has congruent diagonals, it's also going to be known as an isosceles triangle. Here I have a parallelogram, and these are the properties of a parallelogram. So if I'm trying to identify a shape as a parallelogram, if I know that opposite sides are congruent, opposite angles are congruent, the diagonals bisect each other, or any of those other qualifications, I can say this is a parallelogram if any of those are true. If I want to prove that something is a rectangle, these are the properties of a rectangle. I'm going to have to make sure that the information that is given to me in the lab problem meets the criteria in the right-hand column for this. This is a great time to take a screenshot and print these out so you have them for easy reference. Here are some additional quadrilaterals like kites. If I have a kite, these are the properties that the kite follows. Again, take a screenshot of this slide so you have it handy while you're working in the lab. A rhombus is going to be unique. A lot of people mistake a rhombus for a square, but in a rhombus, I don't have 90-degree angles. That's not a requirement for a rhombus. In a square, you have fewer properties because the square has a very specific shape and it does require 90-degree angles. So here's an example where I want to prove that a quadrilateral has diagonals that are congruent and bisect each other is a rectangle. So if I look at this quadrilateral, it's showing me that the diagonals are bisected, and I must know that one of those has to be a right angle in order to prove that it's going to be a rectangle. So if I look at the two angles, I know they're supplementary because it's a parallelogram. So then I also know that these are congruent by side, side, side because the opposite sides of the rectangle are congruent, and then the diagonals are also going to be congruent. So therefore, I know that BAD has to be equal to CDA when I'm looking at the angles. Since those angles are supplementary and congruent, they have to be a right angle. because if they're congruent, the only way to get to 180 is to add 90 and 90. In this figure, I have a right triangle, and it's being told to me as a right triangle, and CD is what they call a median, or a segment that's going to go from the vertex to the middle of the opposite side. If I want to prove the median is a right triangle and is half as long as the hypotenuse, I'm going to go through a list of some additional information. Well, I know that C is a right angle, so you might want to draw that on there. And if D is the midpoint of AB, which I know it's the midpoint because it's the median, then I just need to prove that 2CD equals AB. So to do that, I'm going to extend this out and create a quadrilateral. From that quadrilateral, I'm going to know that D is the midpoint from knowing that it's a median. So I know the diagonals are bisecting with what's going on here, which tells us that ACBE is a parallelogram. So since C is a right angle from the earlier information, ACBE would have to be a rectangle because it has bisected diagonals and it has right angles. If I want to look at the congruence of quadrilaterals in other figures, one way to determine a quadrilateral is to give directions for drawing it. So if you would start with a slide and tell by what angle to turn it at each side to draw the next side, that's going to be considered using the exterior angle. So therefore, if we look at this, side angle side has a valid congruence condition for quadrilaterals as well as angles. So I'm looking that I have three congruent sides, and the angles between them are also congruent in a quadrilateral, and that can be used to prove the congruence of two quadrilaterals.